So we're going to go over something called optimization problems, section 4.7. Yeah, 4.6. I'll talk about that at the end of class, what I want you to know from 4.6. But for 4.7, these are good applied problems. And there's a few things that I'd like you to do when you're working through these. And it's how I'm going to grade you, too. I'm going to look for you to draw a picture. You know, a picture is worth 1,000 words, and it's worth points on your exam. So draw a good picture, label it, try and put in some variables, try and find some relationships, etc. And the picture is going to help you create a function. So now that function is what we're eventually going to optimize. We're either going to minimize it or maximize it, but it needs to be a function of one variable. This is Calc 1. It's not multivariable calculus. We're just going to try and deal with something that depends on one variable. Now that's going to mean that you're going to need to take advantage of relationships and try and whittle things down so that it just depends on one variable. That function is going to be defined over some interval. And that interval is going to make sense to the problem. Essentially, it's going to be the domain for the problem. Where are you going to optimize that function over? What values? And last but not least is the analysis. That's where you do your calculus, where you're going to try and find a minimum or a maximum, and that involves taking derivatives. You can also look at second derivatives if you want to or need to try and decide, do you actually have a minimum or maximum, whatever you need. But those are the 4 steps, and that's what I'm going to be looking for when I grade your assignments, when I grade your exams, these things, and I'll break up into points from there. So let's start with looking at problem number 6. And I do have a nice little visual demonstration of that. Pull that out as soon as we look at the problem. It says, what is the minimum vertical distance between the parabolas? We got these two parabolas, x squared plus 1 and x minus x squared. So what's the minimum vertical distance? Well, to help with that, let's take a look at the first one of our desmos links. So this would be section 4.7, part 1. And if you have this open, you might want to go to the tool setting and click projector mode. And here's our 2 parabolas, one in blue, one in green. And what we want to do is we want to try and find the value of x that makes the distance between these, the vertical distance, as small as possible. So, what do I mean by that? Well, if I move this vertical line, then it could get closer, it could get farther. And let's do that. Let's move this vertical line. So this is where your part comes in. So you move that vertical line. Ooh. And then the other one. All right, good deal. All right. So what you're trying to do is you're trying to find the spot where that vertical line is the shortest. So where is that? Well, we can kind of get kind of close. And you can see the distance here. I created this little metric D. And you want to try and make D as small as possible. And you can kind of play around and say, okay, you know, around 0.88, that's looking pretty good. But to actually get it as small as possible, we're going to need to use calculus. But at least visually, I hope you see what's going on here. We're trying to make that as small as possible. So let's flick back to our handout. We've got a picture. That's already done. So let's look at coming up with a function. Other way around. So our function, what we want to do is we want to minimize the distance between those two. And our functions were what? Y equals x squared plus 1 and y equals x minus x squared. Now how are you going to calculate the distance between two things like that? Well, this is our f part. So that distance is really going to be the top function minus the bottom function, right? It's just going to be the difference in the y coordinates. So let's just give it a nice top minus bottom. That's going to be the distance between those two. So you're just going to subtract the y coordinates. And let's confirm our intuition on that. So right here, I'm at this point, say 1.04. And down here, I'm at another point, say 0.19. The distance between these two is just the difference in the y coordinates, 1.04 minus 0.19. So that's what we're trying to minimize, is that distance. Well, if I wanted to call this, say, y1 and y2, then it's just going to be the difference, y1 minus y2. But it'd be handy if that was defined in terms of x. So I'll call that x squared plus 1 minus x squared. So instead of just the y coordinates, now I've got the x coordinates, and I want to minimize this distance. Well, what's nice is that that is a function of just one variable. So I call that distance, instead of just d, let me call it d of x. Can we clean that up a little bit? Yeah. If you distribute the negative, x squared plus 1 minus x plus x squared, it cleans up into 2x squared minus x plus 1. And that's our function. That's what we want to try and minimize, because we want to try and find the minimum distance there. Okay. Picture function interval. Are there any natural restrictions on x? Is there any limit to what x could be? No. And if we look back at the graph, I mean, we can kind of see that there's really nothing that, prevents us from choosing a value of x way out to the left or way out to the right. Although we kind of think it's going to be in here is our value of x. But as far as the domain of this, or the interval over which this is defined, negative infinity to infinity. Or some of you like script r. That's fine too. Now we get down to the calculus part, the analysis part. So for the analysis part, we want to try and find where this is a minimum. So how can we do that? How can we find where this is a minimum? Yeah. Start by calculating the derivative. So d prime of x, help me out with that. What would that be? 4x minus 1. And I want to know where that's equal to 0. And I hope you can see that that's at 1/4. Now, a good thing to determine is that 1/4, is that actually a minimum? Because sometimes these critical points can be maximums as well, right? So there's two ways that we can show that this is a minimum. One of them is with the first derivative test, x, d, and d prime. And this is actually going to be harder than the second derivative test, but at 1/4 it's 0. Now to the left of 1/4, if I put in a value of x to the left of it, say 0, what's the sign of this going to be? 0 times 4 minus 1 is going to be negative. So the function is decreasing. To the right of 1/4, say x equals 1. 4 times 1 minus 1 is 3, so that's positive. So if you have something that goes from decreasing to increasing, then that critical point has to be a local min. So that's the first derivative test. But the second derivative test, and this one actually works out a lot faster. What's the second derivative? That's 4, right? And at 1/4, which is our critical point, well, the second derivative is greater than 0. that means it has a concave up shape there, so that any critical point has to be a minimum. So the second derivative test actually works out really nice here. So this is your minimum. Let's actually go back and check that just for giggles. What you can do with this is actually type in the exact value, say 0.25. Oops, 0.25, and there you go. So the closest you can get is a vertical distance of about 0.875. So nice, and that's the minimum that you can achieve. How are we looking on that first one? What you'd have to do is you'd have to plug in the value of 0.25 into the top function, and then plug into the bottom function, and subtract the two vertically. So the top one is up here at about 1.062, and the bottom one's down here at about 0.19. Now these are approximate values; they're rounded, but then you just subtract those two, and that will give you that difference. But it's programmed in here for you on Desmos. This is a nice warm-up example because it's got everything here, and it's pretty easy to see a lot of the different parts of this. And like I said, I'll break up the points on each problem to points for drawing a good picture if necessary, coming up with a function. That's definitely some points. Look at the interval and then do the analysis. I might even give bonus points if somebody actually proves that this is a minimum point or a maximum point per the problem. So most people just get their answer. It's like, oh, good, I'm done. Any follow-up on this? We okay with problem number 6? All right. Well, I don't have a nice swank-looking Desmos picture for the next one, so we're just going to do problem number 14 without one. I don't want to spoil you guys too much. Okay. So here we go. Problem number 14. So we want to find a box with a square base and an open top to have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. So there's a couple things going on here. And I always marvel at how much information they can pack into such a little space. There's a lot here that we actually need. So let's start with a box. And I'll draw ourselves a really cool box. So let's do that. Here. There. That's why I went to graduate school, to draw boxes. There we go. Alright, so, and then give a little perspective back this way. I hope you know the formula for the volume of a box. What's the formula for the volume of a box? I mean, there's other objects that like a cone. Okay, that's 1/3 pi r squared h. But I don't expect you to know that one off the top of your head. A box, I think I expect you to know that one. All right. So some help on that one? Length times width times height. Yeah. So length times width times height. Yeah, that one I expect you to know, but some of them get a little bit, out there, and I don't expect you to know all of them. I'll help you out with that, just like I did in the last test with the volume of a cylinder. Okay, now they tell us that the volume is 32,000 cubic centimeters. So that's our picture, and we're working on trying to find the function. But remember what we're trying to find So we're trying to find the size of this box that minimizes the surface area. And they told us something important about this box. It says it's a square box. So that means the bottom has to be X here, and it has to be X here. Now, the only thing we don't know is how tall it is. But it's got to be tall enough so that the total volume of this is 32,000 cubic centimeters. Okay. There's one other thing about this box. Remember they said that there's an open lid here. So it's open at the top. So the material needed to make this is really the four sides plus the bottom. So we need to come up with a function that represents the surface area. So I'll call that S. And that's going to be a combination of the area of the bottom plus what else? Area of the four sides. And I kind of like taking this big picture approach. Don't try and write down the exact function in one step. If you do, it's going to drive you crazy. Think of it in bigger chunks and then refine it. So this is kind of like our first level approach. All right, it's the area of the bottom plus the area of the sides. Well, let's refine that now. Let's start with the area of the bottom. What's the area of the bottom? X squared. Plus the area of four sides, so it's going to be 4 times what? That's actually an H. Yeah, no, sorry. All right, but you're right. So the area of the side here is going to be X times H. So X times H. So that's pretty good. I'm still going to call this S. Now, if you remember at the start of this, I said that we need to write this as a function of one variable. How many variables does this depend on now? 2. So we're in a little bit of a jam, but we do have this relationship right here. 32,000 equals length times width times height. And in fact, I can make that a little bit better, because the bottom two dimensions, length and the width, are X and X. So X times X is going to be X squared times H. How could I solve for H here? I've got 32,000 equals X squared H. So what does H equal? 32,000 divided by X squared. And that's perfect. That's exactly what I needed, because that's going to go in over here like that. Let's see what that gives me. That's going to give me X squared plus 4X times 32,000 over X squared. And we can clean that up a little bit. That's going to be X squared plus 128,000 over X, because one of those X's is going to cancel. This is exactly what I wanted. Now up here I was calling that S. The distinction I want to make now is that this just depends on one variable. So I'm going to call that S of X. That's what I was looking for. I wanted a function that depends on just one variable. So there's that function. How are we looking on that one? Okay there? All right. Picture, function, what comes next? Interval. Now we got to look at our problem and decide, well, Are there any natural restrictions on x? Can x just be anything? Certainly can't be 0. There's one other restriction I guess I'd put on x. Exactly. So our interval has to be 0 to infinity. So when you're trying to maximize this or minimize this, then what you're going to want to do is try and minimize that over the interval 0 to infinity. Now I guess there's one last thing I'll do here. S of x is x squared plus 128,000 x to the negative first power. Why did it do that last step? Quotient rule. Yeah, I didn't want to do the quotient rule at that last step, so I decided, you know what, it's just easier to do it this way. So picture function interval, last step is analysis. So s prime of x would be 2x minus 128,000 x to what power? Negative 2. And I want to know where that equals 0. I want to know where the critical points are. So let's set that equal to 0. 0 equals 2x minus 128,000 x to the negative second. You know, that's a good question. Minus 128,000. You could really think of that as over x squared. And what I'll do here is I'll just multiply everything through by x squared. That way I clear out the denominators, which is pretty much like what you were suggesting. So if I multiply by x squared everywhere, then I get 0 equals 2x cubed minus 128,000. And that's looking a lot friendlier. Okay. Let's move the 128,000 to the left-hand side. 128,000 equals 2x cubed. Divide by 2. And how do you solve? Cube root of both sides. I'm thinking that the cube root of this is going to be 40. Cool. Now we're almost done. And you're looking at me like, what do you mean, almost done? Aren't we done? No. Because remember the problem asked for the dimensions of the box, right? This is just the base. How are we going to find the height? Yeah, you're going to go back up to here, right? 32,000 divided by x squared. Drew? Yeah, we probably should take a moment and look at see if this is actually a critical point. So, trying to think what would be the easiest way to do that. We could do that with a second derivative test. So, let's take a look here quickly at the second derivative. S double prime of x would be 2 minus, actually 2 plus, what, 256,000 x to the negative third, which I'll write over here as x cubed, right? Now, I'm not actually going to calculate this out. S double prime of 40, well, this is positive, and 256,000 divided by 40 cubed is also going to be positive. So what's that say about our critical point then? The shape here is concave up, so this has to be a minimum. So therefore, 40 is a minimum. Nice. Thank you. Let's finish this up. H is going to be 32,000 divided by x squared, which is 32,000 divided by 40 squared, and I'm thinking that's going to be 20. Someone want to check me on that? So 40 by 40 by 20 will be the overall dimensions. Nice. Okay. Any wrap-up you'd like me to do on some of this? There's a lot that goes on these. That's why I limit myself to only 8 or 10 of these on an exam. All right. These are going to be challenging. I won't kid you on this. So let's keep going. Classical problem is problem number 18. That one seems to be a favorite amongst calculus authors, and our current text is no exception. So let me put problem number 18 up. And then for this one, I do have a really stunning desmos demonstration. I think you'll like it. The fence one, yeah. So a farmer wants to fence in a regular rectangular plot of land adjacent to the north wall of his barn. It's interesting that they use the north wall, which doesn't really matter. Usually math problems don't waste words, but they did in this case. That's okay. No fencing is needed along the barn, and the fencing along the west side of the plot is shared with a neighbor who will split the costs of that portion of the fence. We're going to ignore that part. If the fencing costs $20 per linear foot to install, and the farmer is not willing to spend more than $5,000, find the dimensions of the plot that would enclose the most area. So like I said, I'm going to ignore the part that says his neighbor is going to split the cost, so that way it'll keep it a little bit simpler. And let's draw ourselves a decent looking picture. Say again? Here we go. Barn. That's beautiful. So here and here. So these two sides have to have the same length. And then you're going to have this side here, which is going to be perhaps a different length, perhaps the same length. We don't know. But there's our picture. And they tell us something about this problem that is helpful. It costs, or he's going to spend $5,000 on this fence, and it costs $20 per foot. So how many feet can he buy? How many feet of fencing is he going to have? 250, right? 250 feet. So that's how much fencing he has. And what that says, in other words, is 2x plus y equals 250 feet. That is, if you add up these two sides, which are the same length, and this side, you got 250 feet worth of fencing. Okay, nice. So that's a little background. We've got our picture, and we're headed towards our function. Now, our function is going to be to find the area, right? So, well, it's just a rectangle. I'm hoping we can find the area of a rectangle. Area of a rectangle is what? Length times width. And in this particular problem, x times y. Well, no, x times y is correct. But the problem with this function is that it depends on two variables, right? It depends on x and y. We want something that just depends on one function. So how could I rearrange this so that it just depends on one function? There you go. So from our little equation up here, I can say that y equals 250 minus 2x. And I can drop that down into our area formula, which gives me something that depends just on x. A of x is x times 250 minus 2x. Nice. That's our formula. Bless you. Now, let's think about our interval next. And I think it's time for that stunning visual demonstration. So let's go over to Desmos for a moment. So come over here. Now we are going to have to resize our window. So let's shut off these graphs first. And then you want to go up here. I think we want to go from negative 125 on the x-axis to positive 125. And then on the y-axis, issue 125. There you go. On the y-axis, we can go from 0. I'm trying to think here. Let's try 150. I think that might work. We can kind of scroll out if we need to. So underneath problem number 18, you should see 3 different graphs. Let's click each of those. 1, 2, and 3. And that fills out our barn, or excuse me, our our rectangular area. The x-axis is our barn. And what we want to do is we want to move this around until we get something that maximizes the area. So there's some trade-offs here, right? I mean, you can make it wider, but then it's going to be shorter. You can make it really tall, but then it's going to be very narrow. So where is it that maximizes this? Where's the sweet spot, happy point? Well, let's think on something else here while we've got this. What are the limits? There are some limits that are imposed by this problem for our interval. So where's our function defined on? What's the smallest that x could be? What's the largest that x could be? If it's 250, well then 2 times 250 is going to be 500, and then you'd have a negative. So we're going beyond that. Yeah, so 125. What about at the other end? What's the other possibility here? What's the smallest that x could be? 0. Should I use brackets or parentheses? I guess it's kind of up to you a little bit. I would use parentheses because when you get to some of these extremes, like 125, there's no height left, right? If there's no height left, then you've got no area. And at the other extreme, there's no width, so again, you've got no area. So for me, for my money, I'd put parentheses around these. Our maximum has to be in that interval. Okay. So the rest of this is the analysis. And by the way, I forgot to do something here. I forgot to get something from you. So hang on a second. All right, we're ready? Ooh. And then over here. All right, thank you. All right, so these are cool. I mean, it's just nice to be able to visualize this. I mean, when I was taking calculus, the instructor said, well, imagine. And you don't have to imagine. It's something you can adjust. So play with it and enjoy it. So the analysis. Let me distribute that. That's going to be 250x minus 2x squared. Why is it a good idea to distribute that? Yeah, if you didn't, then when you're doing the derivative, you'd have to use the product rule, which would be annoying. So let's find the derivative here. derivative be? 250 minus 4x. Cool. So, all right, so we set that equals 0. We get 250 divided by 4 equals x. So that's what, 62.5? So with that width, what's this distance? Well, our y value would be 250 minus 2 times 62.5, so that'd be 125. Okay. Yeah, so we can verify that this is actually a maximum point, that is the maximum area, by looking at the first derivative test. So you can look at the sign as you pass from to the left of 62.5 to the right of 62.5. And if it's a maximum, it should go positive and then negative. But probably an easier way is to do the second derivative. So what's the second derivative here? Negative 4, which is less than 0. So what shape does our function have at this point? Concave down, which means that our critical point is actually a maximum point. So 62.5 is a maximum using the second derivative test. The second derivative test can be really nice, makes it pretty quick. How are we looking on problem number 18 here? Okay. Has anyone ever heard of something called a Norman window? All right. Yeah, I hadn't either until I started teaching calculus. So that's going to be part of our next problem. It's going to be problem number 30. That much I have heard of. Yes. Yeah. No, I like that. You remember that. Narcissistic numbers? Yeah. What's amazing is there's only 88 of them. 8,208, I think, is one. 2808. Check me on that. All right. So let me switch over here for a second. Boy, I hope this didn't freeze as we're recording it. Problem number 34. So we have a Norman window. Has a shape of a rectangle surmounted by a semicircle. So basically you're going to put a half circle on top of a rectangle. If your window has that shape, and if you're limiting the perimeter of the window to 30 feet, find the dimensions that allow the greatest possible amount of light to be admitted. So let's see. I don't know if I have anything fancy I'll draw a little semicircle with. No. This would be pretty big, but okay. Whoops. Walk into my voicemail. All right. So, hey.
That was easy.
Cool. All right. So, let me go back here. There. All right, so this is problem 34. And then we'll draw a little base like this, down here, then over. This is called a Norman window. So you have a semicircle on top of a rectangular base. So there's our picture. And we should probably label our picture a little bit. And so let me think how I want to do this. I'll do it this way. Since the area of the top of this, or the perimeter of it, is going to be defined in terms of r, the radius, I'm going to call this distance here x. So that means the bottom, how wide is the bottom? 2x. And then this distance, I don't know, it's something else. That's going to be the height. So that's our setup as of the moment. So 2 points for our picture. We've got it drawn correctly and labeled it right, so we're looking good there. Picture, function. Now ultimately what we want to do is we want to design this window with that fixed perimeter so that we can emit as much light as possible. So let's see here. The amount of light that comes in is going to be the area of the top half plus the area of the bottom half. So area equals area of the top half plus the area of the bottom. And we're going to just think of this in nice general terms for the moment. How do you find the area of the top? All right, not quite. You're thinking of the circumference. What's pi r squared? But we don't have a whole circle, right? Divide by 2, yeah. So area of the top is going to be 1/2 pi r squared. Actually, in this case, it should be pi x squared, right? Because I define the variable x to be our radius. So pi, we're going to make that an x squared, right? Because our radius is x. How about the area of the bottom? What's the area of the bottom? Yeah, 2x times h. So that's our area. But like all these problems, we've got to eliminate one of the variables. Which one do you think we're going to eliminate? H. Yeah. To eliminate h, we need to use something else that the problem told us. And what the problem told us is that the total distance around this, the perimeter, is 30 feet. So that's what's going to help us get rid of the h. Now, I'll give you a heads up. The expression that we'll end up with is going to be kind of ugly. And, you know, it's just what we're going to have to deal with. That's okay. Let's see here. The perimeter, well, that's going to be a couple parts. It's going to be h plus 2x plus h plus half of a circle. How do I find this part of the circle? That perimeter of the circle. Pi r squared is the area? 2 pi r. There. Yeah, there you go. So 2 pi r divided by 2, or in our case, 2 pi x divided by 2. And this is going to clean up a lot. I've got h plus h. That's going to be 2h plus 2x plus pi x. And that perimeter is fixed, right? What's that perimeter equal to? 30. So let's solve for h. That means moving this term and this term to the other side. So 30 minus 2x minus pi x equals 2h. Almost there. And it's just not really a pretty function. not much I can do about it. But that is what we're going to put in up here for H. At least one nice thing is going to happen. This 2 here and this 2 here are going to cancel. So, okay, we'll get a little bit of a break there. So we'll call it A of x, because we're getting rid of the h here. This is our function of one variable. It's going to be 1/2 pi x squared plus 2x times 30 minus 2x minus pi x over 2. And as I said, the x's or the 2's will cancel. One half pi x squared plus, let me distribute the remaining x. That's going to be 30x minus 2x squared minus pi x squared. There. Now, even though it doesn't really look like it, there are like terms here that I can combine. Does anyone see them? So these two are like terms. I've got negative one of them here and a plus 1/2 here, so I end up with negative 1/2. So overall, this is A of x equals 30x minus 2x squared minus 1/2 pi x squared. Yeah, beauty, eh? So that was a little bit more work than some of our other ones, but the idea is still the same. You're still trying to find a function of one variable. So, wow. Well, before we do the derivative, let's get to another ooh-ah moment, all right? So we can click back here over to Desmos. I'll shut these off. And let's see. I want to turn these ones on. I'm going to need to zoom in. So we'll zoom in a fair amount here. But what's going on is, again, there's a trade-off. There's a trade-off between your perimeter and the area. So if you adjust the slider, you can see what's going on. You can make it taller and narrower, or you can go to the extreme. You can make it all just the semicircle in the window. But actually, that's too far. We've gone too far here because to get up to here, we'd be using more material than we have. So somewhere in here, though, is a nice happy medium. And you can kind of judge that a little bit with this function down here. So you can move it around and try and make that as big as possible, up into the 50s, 60, and then I'm starting to go the other way. So somewhere close to here looks like it'd be the maximum, even though it's kind of tough to see. Let me kind of zoom in a little bit, but you can judge it by this function here, which gives you the area. That's exactly what we have for ourselves. So the question is, what allows the maximum light? How big should I make that radius? Well, let's go back and do some calculus here. Now, without working too hard for our interval, we only have 30 feet to work with. So the most that this could be, actually it's not even that, but an easy place to draw a cut line is like, okay, if I had no radius and everything was height, then the most that I could be is 15. So 0 to 15. It's actually less than that. Would be the correct value, but that's a good guide. And again, we're not using either of these extremes. We don't want a window with no width. We don't want it to be all up top either. So it's going to be somewhere in here. But let's work on the analysis part. The analysis part, no, it's not too bad. Let's work on the derivatives here. A prime of x. I'll give you a chance to differentiate a before I put it up there. So what'd you get? 30 minus... Excellent. So to find the critical point, I want to know where that's equal to 0. 30 minus 4x minus pi x. If I move these points to the other side, or these terms to the other side, then 4 plus pi x equals 30. X equals 30 divided by 4 plus pi. So that value of x should be the value of x that maximizes the area. You can calculate that on your calculator. Should be about 4.2 is what I'm getting. We should go back and test that this is actually a maximum point. Or wait, trying to maximize or minimize? We're just trying to maximize the area going through there, right? Yeah. Okay, so if we were to look at the second derivative, a double prime of x would be minus 4 minus pi, and that's always less than 0. So the shape of the function is going to be concave down at that critical point, so you've got a maximum. Nice. So that's going to be the radius. That's that value of x way up here. Wow. You guys are going to have fun this weekend. I envy you. Any follow-up on this? Something that I can help out with? Something else I can help out with. Okay. Let's do one more. Problem number 24, and I've got a different link for this one, so I had trouble getting everything in one link here. So the problem in problem 24 is this. You've got this point at 4, 2, and you want to figure out what point on the curve of the sine of x is closest to the point 4, 2. So we can kind of adjust this around a little bit, play around with that, move it around, and you know, it looks like the closest point is going to be about there, right? So this point right here, or about here, is going to be closer than any other one to the point 4, 2. Yeah, somewhere around there, somewhere around 2.6. But how do we prove this, and how do we find the exact closest value? So, by the way, I forgot. One more time, last time. All right, well done, thank you. All right, so Well, if I'm trying to find the closest point, then I'm trying to minimize what? I'm trying to minimize the, somebody give me the distance, right? So let's work with the distance formula. And let me get back over to here. We've got problem 24. We've got the point 4 and 2. And y equals sine of x. I want to minimize the distance between those two things. So our picture was on desmos. We're going to work on the function next. Does anyone remember the distance formula? All right, good, thank you. So x2 minus x1 squared plus y2 minus y1 squared. Yeah, the square root of that. All right, well, the unfortunate thing is that this depends on two variables. So I've got a point here, call that x1 and y1. And over here, I've got another point, call it x and sine of x. And that's my x2 and y2. So if I put these two in here, then I'll eliminate the dependence on two variables. I'll just have one variable, which would be x. So we'll call it d like that. So it's going to be x minus 4 squared plus sine of x minus 2, again squared. And that actually depends on one variable. So I'm okay here. But as far as the calculus is concerned, minimizing the distance or minimizing the square of the distance will give us the same thing. So to make it easier on us, we're going to call this d squared. We're going to square both sides of this and get d squared, which is going to be x minus 4 squared plus sine of x minus 2 squared. And, okay, this is the function that we're going to work with. We're going to minimize this distance here. It's just a lot easier than working with the square root. You'll get the same thing. It's just the calculus is going to be easier because you won't have to use a chain rule for the square root function in addition to using the chain rule for these things. I don't know. Let's call this a different name. Does anyone want to suggest a different name? I don't like d squared of x. Let's see. We'll call it k of x. Katie, is that okay with you? All right, that's good. All right, so k of x. K of x is x minus 4 squared plus sine of x minus 2 squared. What comes next, Brandon? Picture, function, interval. Well done. Well done. Thank you. So let's see if we can't figure out the interval. Are there any restrictions on the value that I choose here for x? Well, this one's fixed, but as far as the other part of this, there's really no restriction on what value of x I choose. I mean, obviously it's not going to be something way out here, right? Because then the distance between these two things is getting really long. And you can see that distance here. And it's probably not going to be way out here, but there's no natural restriction that I can see. So as far as the interval, I see that the interval is negative infinity to infinity, or all real numbers. Okay, let's get down to the part that we do with all of these problems. If there's no calculus on these problems, I'll just tell you now, you've done it wrong. There's going to be calculus involved in every one of these. I always get people that hand in tests that don't have a derivative or anything like that, and I just like, wow, I promised you would have to use calculus. You have to use calculus on these things. That's the only way you're going to solve them. So let's do the analysis. The analysis is going to involve some calculus. k prime of x. Why don't you differentiate this and see what you can get? Are you using the chain rule? Check with your neighbor. See if yours matches your neighbor's. Nah, I'm not gonna make you distribute. Nah. No, there's a kind of a nice tie-in with something else that we'll do here next, but I'm not gonna make you distribute. So we're getting good agreement amongst you guys? Great minds think alike, or fools seldom differ? Which one is it? All right. So the derivative here is going to be the derivative of the outside, which is 2 times x minus 4, times the derivative of the inside. What the derivative of the inside is? 1. Good. Plus 2 times sine of... Wait a minute. You got to save those. 2 times sine of x minus 2. That's the derivative of the outside. What's the derivative of the inside? Cosine. Well done. Cosine of x. Here comes the fun part. Here comes the fun part. You can set that equal to 0 and solve. Woohoo! Yeah, good luck on that one. Now, this is kind of cool because I can do some advertising for my next video. Woohoo! Which is Newton's method. We're not actually going to solve this one algebraically. Honestly, I don't know how you would solve it algebraically. You're going to use what's called Newton's method, which is a numerical approach to solving these things. You can solve this graphically on your graphing calculator, but we're going to solve this one in the next section with Newton's method. Yeah. Please stay tuned for a message from our sponsors. X equals, it's about 2.651. And that's going to be our minimum point. Let's just double check it on desmos. At least we can do kind of a visual double check. If I make this 2.651, now watch what happens to that Q of S. Here I'm at 2.6 and 2.65, and the number gets smaller, 2.651, got a little bit smaller. So yeah, it looks like we're hitting the minimum point on that. So at least Newton's method seems to be steering us in the right direction. And like I said, we'll get a nice demonstration of that in a little bit. I do have one more problem that I want to do for optimization here, but I think I want to take a break first. Before I do, Christian? I just gave this a new name. Yeah, I squared both sides here because when I maximizing this function is going to give you the same maximum as this one. So I just didn't want to have to deal with the derivative of this because that's just going to be one more layer of complications. It's just going to be a bigger mess. So it's easier to maximize the square of the distance as opposed to the distance. So it's just doing it for the sake of the calculus, ease of calculations. Yeah. No, because I mean, this distance is still going to be the minimum either way. If you're minimizing the square of the distance or the distance is still going to represent the minimum distance. Yeah. This is finding where that minimum occurs. It's not telling you what that is. If you're trying to find what that distance is, then you would have to use the square root. Yeah. All right. We good with both of those? Jeanette? All right, so yeah, the derivative k prime. All right, so yeah, so I just gave this a different name. I squared both sides, and I didn't want to use a d squared here, so I just called it k of x. Yes, this one. Yeah, I just renamed it. Okay. No, I just renamed it because, and I wanted to be able to take the derivative, and I didn't think it would look good if I had d squared prime. I just thought that would be really confusing. So, Katie donated the name of this function for us, and we were good. Okay, we'll do one more here in a minute, but let me give you a break first, and we'll come back and build a better can.